In this section, I'm going to be considering the Laplace transform and its relationship to LTI systems. We'll see how an LTI system can be characterized in the Laplace domain using the system function of the system, and we'll examine various aspects of the system function in more detail. Lastly, we'll consider the family of LTI systems that are characterized by linear differential equations with constant coefficients. For such systems, we'll see how the differential equation representation of the system is related to its system function. Suppose that we have an LTI system with input little x, output little y, and impulse response little h, and let big X, big Y, and big H denote the Laplace transforms of little x, little y, and little h respectively. We know from earlier that an LTI system is characterized by an equation of this form. In other words, an LTI system is such that the output of the system, which we denote as little y, is equal to the input of the system, which we denote as little x, convolved with the impulse response of the system, which is denoted as little h. If we take the Laplace transform of this equation using the convolution property of the Laplace transform, we obtain this particular equation here. In this equation, the function big H is referred to as the system function or transfer function of the system. In other words, the Laplace transform of the impulse response is called the system function. The system function is extremely important because it completely characterizes the behavior of an LTI system. In other words, if we know the function big H, we can determine for any given input the output of the system. In particular, if we're given a system input little x, we can find the Laplace transform big X of little x, then multiply by the system function big H to find the Laplace transform big Y of the output. Then by taking the inverse Laplace transform of big Y, we can find the system output little y. This equation also provides an alternative way to view the behavior of an LTI system. In particular, we can view an LTI system as computing the product of the Laplace transform of the input of the system and the system function to yield the Laplace transform of the output of the system. Lastly, recall that if the region of convergence of the Laplace transform of a function contains the imaginary axis, then the Fourier transform of the function is obtained by evaluating the Laplace transform on the imaginary axis. For this reason, the frequency response of an LTI system is obtained by evaluating its system function big H on the imaginary axis, assuming that the imaginary axis is contained in the region of convergence of big H. Often block diagrams provide a very convenient way in which to represent systems. When dealing with LTI systems, it's often beneficial to represent systems in the Laplace domain. When drawing block diagrams that correspond to a Laplace domain representation, we often label each of the LTI systems with their system function. The system function makes a good label for an LTI system, since an LTI system is completely characterized by its system function. For example, we can use a diagram like this one here to denote an LTI system whose system function is big H and whose input has the Laplace transform big X and whose output has the Laplace transform big Y. Earlier in the course, we were introduced to two basic ways in which systems can be interconnected. In particular, we looked at series interconnections and parallel interconnections of systems. What I'd like to do on this slide is revisit these two types of interconnections in the context of LTI systems that are represented in the Laplace domain. First, let's consider series interconnections. Earlier in the course, we saw that the series interconnection of two LTI systems behaves as a single LTI system with an impulse response equal to the convolution of the individual system impulse responses. From this, we can infer the following by using the convolution property of the Laplace transform. The series interconnection of LTI systems with system functions big H1 and big H2 is the LTI system with system function big H1 times big H2. In other words, when LTI systems are connected in series, their system functions multiply. Now let's consider parallel interconnections. Earlier in the course we saw that the parallel interconnection of two LTI systems behaves as a single LTI system with an impulse response equal to the sum of the individual system impulse responses. From this, we can infer the following by using the linearity property of the Laplace transform. The parallel interconnection of the LTI systems with system functions big H1 and big H2 is the LTI system with the system function big H1 plus big H2. In other words, when LTI systems are connected in parallel, their system functions add. Earlier in the course, we were introduced to a number of properties that a system can possess, such as causality, BIBO stability, and invertibility. Previously, we also saw that an LTI system is completely characterized by its system function. Therefore, anything we could ever want to know about an LTI system must be embedded into its system function. So for an LTI system, in principle, it must be possible to tell from the system function of the LTI system whether the system is causal, BIBO stable, invertible, and so on. Practically speaking, however, the more interesting question is whether such information can be easily extracted from the system function. As it turns out, this information is often very easy to extract. So what I'd like to do on this and the next few slides is consider how we can characterize various system properties in terms of the system function in the case of LTI systems. First, I'd like to consider how the causality property can be characterized in terms of the system function of an LTI system. Recall from earlier in the course that an LTI system is causal if and only if its impulse response is causal. Therefore, a causal LTI system always has an impulse response that is causal, which further implies that the impulse response is right-sided. Recall also that a right-sided function, which may or may not be left-sided, must have a Laplace transform whose region of convergence is either a right half-plane or the entire complex plane. Therefore, we have the result stated in the first theorem on this slide, which reads as follows. The region of convergence associated with the system function of a causal LTI system is a right half-plane or the entire complex plane. In other words, the causality of an LTI system implies that the region of convergence of the system function is either a right half-plane or the entire complex plane. The converse of the preceding theorem, however, is not necessarily true. That is, if the region of convergence of the system function is either a right half-plane or the entire complex plane, it is not necessarily true that the system is causal. If the system function is rational, however, we have that the converse does hold, resulting in the second theorem on the slide, which reads as follows. For an LTI system with a rational system function big H, causality of the system is equivalent to the region of convergence of big H being the right half-plane to the right of the rightmost pole, or, if big H has no poles, the entire complex plane. In other words, as long as the system function big H is rational, the region of convergence of big H being either a right half-plane or the entire complex plane is equivalent to the system being causal. Since system functions are frequently rational in practice, this second theorem is often applicable. At this point, I'd like to consider an example to show how we can make use of the theorems presented on this slide. In particular, I'd like to consider example 7.31. In this example, we're given four linear time invariant systems, each with the system function denoted by big H, and we're asked to determine whether each of these systems is causal. More specifically, the four functions for big H that we're asked to consider are the four functions that are given here. First, let's consider the system function big H given in part A. In other words, let's consider this particular system function here. Clearly, big H is rational. The poles and region of convergence of big H are plotted in figure A, in other words, this figure here. Since big H is rational with one or more poles, we know that the system is causal if and only if the region of convergence of big H is a right half plane to the right of the rightmost pole. Clearly this condition on the region of convergence of big H is satisfied. Therefore the system in part A is causal. Next, let's consider the system function big H given in part B. In other words, let's consider this particular system function here. Clearly big H is rational. The poles and region of convergence of big H are plotted in figure B, in other words in this figure here. Since big H is rational with one or more poles, we know that the system is causal if and only if the region of convergence of big H is a right half plane to the right of the rightmost pole. The region of convergence of big H, however, is a vertical strip. Therefore the system in part B is not causal. Next, let's consider the system function big H given in part C. In other words, let's consider this particular system function here. Clearly big H is not rational due to the exponential function in the numerator for the expression for big H. In other words, this exponential function here. Thus, all we can say is that in order for the system to be causal, the region of convergence of big H would need to be either a right half plane or the entire complex plane. We can see, however, that the region of convergence of big H is this particular set here. In other words, the real part of S is less than -1, which is a left half plane. Therefore, the system in part C is not causal. Lastly, let's consider the system function big H given in part D. In other words, let's consider this particular system function here. Clearly big H is not rational due to the exponential function in the numerator for the expression for big H. In other words, this exponential here. Since big H is not rational, we can't make any direct conclusion as to whether the system is causal. So in this case, we proceed to test for causality using the time domain. We find the inverse Laplace transform little h of big H and test if little h is causal. As it turns out, little h is given by this particular formula here. Since little h is not causal, the system in part D is not causal. Next, I'd like to consider how the BIBO stability property can be characterized in terms of the system function of an LTI system. As it turns out, the BIBO stability of an LTI system depends on the region of convergence of its system function. In particular, we have the two theorems stated on this slide. The first of these two theorems reads as follows. An LTI system is BIBO stable if and only if the region of convergence of its system function big H contains the imaginary axis. The result of this theorem can be partially justified as follows. Due to the relationship between the Laplace transform and Fourier transform, the region of convergence of the Laplace transform of a function containing the imaginary axis is equivalent to the Fourier transform of that function converging everywhere. Therefore, the condition that the region of convergence of big H contains the imaginary axis is essentially saying that the frequency response of the system is bounded. If the frequency response were not bounded, there would exist some complex sinusoid that we could present to the system as input that would yield an unbounded output, meaning the system would not be BIBO stable. This explains why it is necessary for the region of convergence of big H to contain the imaginary axis in order for the system to be BIBO stable. If we happen to know that an LTI system is causal and its system function big H is proper rational, then the preceding theorem can be made more specific about the form of the region of convergence for BIBO stability. In particular, we have the second theorem stated on the slide, which reads as follows. A causal LTI system with a proper rational system function big H is BIBO stable if and only if all of the poles of big H lie in the left half of the plane. In other words, all of the poles have negative real parts. Note that this second theorem can be deduced by using the first theorem on the slide and our knowledge of how the causality of a system manifests itself in big H. Lastly, it's worth noting that due to the two theorems presented on this slide, determining whether an LTI system is BIBO stable is a trivial exercise if the system function of the system is known. For this reason, the Laplace transform is often used for analyzing the BIBO stability of LTI systems. At this point, I'd like to consider several examples to show how we can make use of the theorems introduced on this slide. First, I'd like to consider example 7.32. In this example, we're given an LTI system whose system function big H has the algebraic expression given in this particular formula here. Then we're told to determine the region of convergence of big H, given that the system is BIBO stable. To begin, we observe that the BIBO stability of the system is related to the region of convergence of big H. So we need to find this region of convergence. Since big H is a rational function, the possible regions of convergence of this function are determined by its poles. Clearly, from the given factorization of big H, in other words, this particular factorization here, this function has poles at -1 and -2. Therefore, big H has three possible regions of convergence, namely these three regions of convergence that are listed here. These regions of convergence are shown in the figure. The first region of convergence corresponds to this purplish shaded region, which is a left half plane. The second region of convergence corresponds to this green vertical strip, and the third region of convergence corresponds to this gray shaded right half plane. Since we're told that the system is BIBO stable, this implies that the region of convergence of big H must include the imaginary axis. Therefore, the region of convergence of big H must be this gray shaded right half plane, to the right of the pole at -1, since this region includes the imaginary axis. Thus, the region of convergence of big H is the region given by this particular formula here. The real part of S is greater than -1. Next, I'd like to consider the example 7.33. In this example, we're given a causal LTI system with a system function big H that has the algebraic expression given by this particular formula here. Then we're asked to determine whether the system is BIBO stable. To begin, we observe that the BIBO stability of the system is determined by the region of convergence of big H, so we need to find this region of convergence. Since big H is a rational function, the possible regions of convergence of this function are determined by its poles. So we factor big H in order to find its poles. Using the quadratic formula, we obtain this particular factorization of big H shown here. Clearly, from this factorization, we can see that big H has poles at -2, -1 minus j, and -1 plus j. Since these poles have two distinct real parts, namely -2 and -1, big H has three possible regions of convergence, namely the regions of convergence shown by the annotated figure here. The first region of convergence corresponds to this purplish shaded left half plane. The second region of convergence corresponds to this green shaded vertical strip. And the third region of convergence corresponds to this gray shaded right half plane. Since we are told that the system is causal, the region of convergence of big H must be either a right half plane or the entire complex plane. Therefore, the region of convergence of big H must be the gray shaded right half plane region here. Since this region of convergence includes the imaginary axis, the system is BIBO stable. Next, I'd like to consider example 7.34. In this example, we're given four LTI systems, each with a system function denoted by big H, and we're asked to determine the region of convergence of big H that corresponds to a BIBO stable system. More specifically, the four functions for big H that we're asked to consider are as given here in parts A, B, C, and D of this example. To begin, we observe that the BIBO stability of the system is related to the region of convergence of big H. So for each of parts A, B, C, and D of this example, we need to determine all the possible regions of convergence of big H. Then, from these possible regions of convergence, we can identify the one that corresponds to a system that is BIBO stable, which would be the one that contains the imaginary axis. Since in each of parts A, B, C, and D of this example, the function big H is rational, the possible regions of convergence of this function are determined by its poles. Furthermore, in each part, big H is given in fully factored form, as can be seen here. So it is a trivial exercise to identify the poles of big H in each case. These poles have been plotted in figures on the next page. So in order to show these plots, I'll now proceed to the next page. The annotated figures A, B, C, and D on this page show the poles and possible regions of convergence for the system function big H, given in parts A, B, C, and D of the example respectively. Let's now consider each of these figures in order to determine the region of convergence of big H that corresponds to a BIBO stable system. First, let's consider part A of the example, which is associated with figure A. In this case, big H has three possible regions of convergence: the purplish shaded left half plane, the green shaded vertical strip, and the gray shaded right half plane. Since the gray shaded right half plane is the one that contains the imaginary axis, this is the region of convergence that corresponds to a system that is BIBO stable. In other words, the region of convergence is given by this particular formula here. Real part of S is greater than -1. Next, let's consider part B of the example, which is associated with figure B. In this case, big H has three possible regions of convergence: the green shaded left half plane, the gray shaded vertical strip, and the purplish shaded right half plane. Since the gray shaded vertical strip is the one that contains the imaginary axis, this is the region of convergence that corresponds to a system that is BIBO stable. In other words, the region of convergence is given by this formula here. The real part of S is between -1 and +1. Next, let's consider part C of the example, which is associated with figure C. In this case, big H has two possible regions of convergence: the purplish shaded left half plane and the gray shaded right half plane. Since the gray shaded right half plane is the one that contains the imaginary axis, this is the region of convergence that corresponds to a system that is BIBO stable. In other words, the region of convergence is given by this formula here. Real part of S is greater than -2. Lastly, let's consider part D of the example, which is associated with figure D. In this case, big H has two possible regions of convergence: the purplish shaded left half plane and the green shaded right half plane. Neither one of these regions of convergence, however, contains the imaginary axis. Therefore, big H cannot possibly correspond to a system that is BIBO stable. Next, I'd like to consider how the invertibility property can be characterized in terms of the system function of an LTI system. In this regard, we have the result stated at the top of the slide, which reads as follows. An LTI system script H with the system function big H is invertible if and only if there exists another LTI system with the system function big H inverse, such that this particular relationship here is satisfied. In which case, big H inverse is the system function of script H inverse, and is given by this particular formula here. Recall from earlier in the course that the inverse of an LTI system, if it exists, is LTI. Furthermore, the impulse responses of an LTI system and its inverse, when convolved, yield the delta function. Taking the Laplace transform of this relationship using the convolution property of the Laplace transform yields the result just introduced at the top of the slide. Note that in the case that the inverse system does not exist, the region of convergence of big H inverse would be the empty set. In other words, big H inverse would fail to converge everywhere. For example, suppose that big H is a constant function equal to 0. Then big H inverse, which is given by 1 divided by 0, fails to converge everywhere, meaning that the system function big H considered in this example would correspond to a system that's not invertible. Since distinct systems can have identical system functions but with differing regions of convergence, the inverse of an LTI system is not necessarily unique. In practice, however, we often desire a stable and/or causal system, so although multiple inverse systems may exist, we are frequently only interested in one specific choice of inverse system, due to these additional constraints of stability and/or causality. At this point, I'd like to consider an example to show how we can make use of the result related to invertibility introduced on this slide. In particular, I'd like to consider example 7.35. In this example, we're given an LTI system with the system function big H in this particular formula here. And we're asked to find all possible inverses of this system and comment on the stability of each of these inverse systems. To begin, we recall that the system function big H inverse of the inverse system is given by this particular formula here. In other words, big H inverse is the reciprocal of big H. Thus we have that big H inverse of S is given by this particular formula here. Now we have to determine all the possible regions of convergence of big H inverse. Since big H inverse is a rational function with a single pole, this function has two possible regions of convergence, namely the left half plane to the left of the pole and the right half plane to the right of the pole. This corresponds to the two regions given by these formulas here. These two regions are shown in the figure included as an annotation. In other words, this particular figure here. In this figure, the first region of convergence, in other words, this one here, is shown as this purplish shaded left half plane. Since this region of convergence does not include the imaginary axis, this region of convergence corresponds to a system that is not BIBO stable. The second region of convergence, namely this one here, corresponds to this green shaded right half plane. Since this region of convergence contains the imaginary axis, this region of convergence corresponds to a system that is BIBO stable. Of all of the types of LTI systems in existence, one class of LTI systems of great practical interest is the class whose members are each characterized by an nth-order linear differential equation with constant coefficients. In particular, each system in this class is characterized by a differential equation of this particular form shown here, where little x is the input of the system, little y is the output of the system, the ak and bk are complex constants, and the integers m and n satisfy this inequality here. Essentially, this equation relates a linear combination of derivatives of the output of the system appearing on the left-hand side of the equation with a linear combination of derivatives of the input of the system appearing on the right-hand side of the equation. Suppose now that for the LTI system defined by this differential equation, we let little h denote the impulse response of the system, and that big X, big Y, and big H denote the Laplace transforms of little x, little y, and little h respectively. One can show that the system function big H is given by this particular formula here. Notice that big H is a rational function. In particular, it's a rational function in the variable s. As it turns out, this is one of the reasons why rational functions play quite an important role in systems theory. At this point, I'd like to consider a couple of examples to show how we can convert between differential equation and system function representations of LTI systems. First, I'd like to consider example 7.36. In this example, we're given an LTI system with input little x and output little y that's characterized by this particular differential equation here, where dk and m are positive real constants and the prime symbol is used to denote derivative. Then we're asked to find the system function, big H, of this system. To begin, we take the Laplace transform of the differential equation that we're given, and in particular we do this using the differentiation property of the Laplace transform. This gives us this line here. Then we factor y of s out of all the terms on the left-hand side of the equation, which gives us this next line here. Then we divide both sides of this equation by this particular expression here, which gives us this next line. Then we observe that because the system is LTI, the Laplace transform of the output of the system, which is denoted big Y, is equal to the Laplace transform of the input of the system, which is denoted big X, times the system function of the system, which is denoted as big H. We can rearrange this equation and solve for big H in terms of big Y and big X, which gives us big H is equal to big Y over big X. So we can observe that this big Y over big X here is equal to big H, which gives us this last line, which is the system function big H that we're seeking. Next, I'd like to consider example 7.37. In this example, we're given an LTI system with input little x and output little y that has a system function big H, where big H is given by this particular formula here, and L and R are positive real constants. Then we're asked to find the differential equation that characterizes this system. To begin, let big X and big Y denote the Laplace transforms of little x and little y respectively. Then we can observe that because the system is LTI, it satisfies an equation of this particular form here. Now we can take the function big H that we're given and substitute it in here, which gives us this next line. Then we can multiply both sides of the equation by s plus r over L, which gives us this next line here. And then we can multiply this y of s factor into both terms on the left-hand side to obtain this next line. At this point, we can now take the inverse Laplace transform of this equation, which gives us this next line quite trivially, simply by using the linearity property of the Laplace transform. And then we can use the differentiation property to actually take the inverse Laplace transform, which gives us this inverse Laplace transform here. Therefore, the differential equation that characterizes the system is this particular differential equation here.